let's start. I'm happy to welcome Marco here today to talk about privacy for location-based and Marco's in the CS department at the University of Colorado, and maybe you want to say something about yourself.
Yeah, thanks, Roy. I got a master's also from the University of Colorado, and right after that I started working at IBM Research, not far from here in Westchester, and ended up working for a year and then doing several summer internships after that. So I've worked on topics from integrating mobile pervasive computing, integrating sensors into smart environments, and one of these projects was actually a privacy architecture for automotive telematics. And again, cars are nowadays a sensor-rich platform where you can extract all kinds of information and conceivably remotely process that for services. So this is how I got interested in the privacy topic, and I've taken that back to school and thought about some of the problems there and came up with automatic resolution control for location-based queries. Now, location-based queries we define as network services that can take as an input the user's current location as determined by a trusted device from the user, then execute a search function and return results back to the user's device. For example, if you have a smartphone, you can go to your favorite search engine, enter some keywords. You see, I'm planning for my future here, and your current location, and then you will receive a list of search results, and as you imagine, you can also display them on a map. Now, notice that these are anonymous queries. At no point do you actually need to enter your name or any identifying information. They are relatively sporadic queries, so a single datum of location information is transmitted to the external service provider rather than a continuous stream of updates. And soon we will have automatic position sensing in these devices and the necessary standards so that external service providers can access that information. Now, the automatic position sensing is driven by government regulation E911 in the US and E112 in Europe. These are standards for emergency service providers to determine the position of a cell phone caller. And there are different technologies for implementing that. One is assisted GPS, which can be on the order of 10-meter accurate. Now, this is actually the case that we're really interested in, not when the user manually inputs his current location, but when devices automatically determine position in a very precise way. And then what about privacy? Who can see that location, and who can see that message content, sensitive content such as toupee or a query for medical clinics? Now, before we go into privacy, let me explain a bit more on what I do not mean by location-based queries. There are two examples here. One is offline position-aware devices. You can think of it as an automotive navigation system or just a GPS receiver that contains maps which are stored locally on the device. And whenever your position updates, it queries the local database rather than connecting to an external location-based service. So there's no network connection, no information is transmitted to an external service provider, and thus there's not really a privacy problem. User studies from Barkos and Day at Berkeley have shown that users can understand these differences and perceive them that way. Now, in that case, since there's no network connection, you cannot update the information, cannot access timely information such as traffic status and things like that. Another example are online continuous tracking services. Here you see a cell phone that is connected to a GPS in a car, and the cell phone itself is then used as an automotive navigation service. The GPS receiver frequently transmits location updates to the external service provider, who computes a route to the chosen destination, and then also monitors the user's progress along this route, and always sends the current next step in the route back to the user's display. So the difference between location-based queries and this is in terms of the frequency of location updates. Queries are a single datum of location, whereas this you can think of as a stream of location updates. And in these cases, there's typically a subscription relationship. You order a service, you have to install some custom software on your cell phone, and you enter more of a longer-term relationship where you can think about the privacy implications rather than just looking at a website and doing a quick query. Now, to understand privacy in these cases, you have to look at what parties are involved and how are these services implemented. Here are two possible architectures for location-based services. On the left is a cell phone-based architecture after the GSM standard, for example, and this standard uses a location broker, an intermediary that is in the deployed in the cell phone network and brokers location information between the user's device and an external application service provider, such as the search engine. Now, in this case, the user would enter a query that sends through a gateway that connects the cell phone network and the internet to the application service provider, who can then request the current location of this cell phone from that location broker, and the location broker can determine position using any of a variety of standards, assisted GPS or enhanced observed time difference, send that information back, execute the query, and return the results. It's also possible, as in this wireless LAN-based architecture here, that the clients themselves determine their position relative to known positions of access points, and then just directly contact the application service provider and receive the results back.
How critical is the position information here?
Critical in terms of what?
Specificity or accuracy of location?
We are thinking of accuracies in terms of about 10 meters are possible, and the more accurate it becomes, the more critical are the privacy implications of that, as you will see on the next.
You're simply assuming that there's some level of accuracy that's provided to you by the system.
I'm assuming that. I will not talk about the positioning technology itself. I'm just looking at the services and how can you ensure privacy in it. Now, since these are anonymous queries, at no point did you provide user information, it appears that there are no privacy concerns. However, imagine you're querying for sensitive information and you're sitting on a driveway in a suburban house somewhere in New Jersey, for example. What the service provider will see is a range of information, and even worse, what he will likely put into his web server log files is a string that looks like something like that. There's a bunch of information here. Part of that is the query string, and part of that is which browsers are being used, IP addresses, and it's also likely that they will put the GPS coordinates or the position information into these log files. Now, the IP address is probably just a proxy of the cell phone gateway where it's going through. Many people are using the same browsers, but the position information here can be very precise and extremely distinctive. You can correlate that information to a satellite image which you can publicly obtain from TerraServer, for example. You could correlate it to geocoded address databases. These are databases that contain, for pretty much every US postal address, the exact geographic coordinates. It depends on how precise these databases are. Tiger Line is publicly available, but I believe only precise on the street level. If you go to commercial vendors, you can get much more exact information. Now if you do that correlation, you can identify, so if a location here is very close to a location in a database, you can identify from which household the query came, and now you have linked that sensitive information to a specific household. There are many other potential sources of location and identity information, such as automatic toll booths, customer loyalty cards, and something we are most worried about is records from other location-based services. What if these services become much more popular? Your privacy policy may say, I trust this service provider, and let him track my location at all times, and he knows my identity. And then once in a while I contact a different service provider where I would like to be anonymous, or I believe I'm anonymous. Later, companies get brought up and they start linking their databases together. Now these anonymous queries are identified. So more generally, the problem I'm talking about is that of linking different data sources. An adversary sees log files from the location-based services that contain location information and sensitive content. He also has access to databases that contain identity and location, and these databases may even be publicly available, such as the household database. Now, if the location information is sufficiently distinctive, you can connect them together and link the sensitive query to a specific identity here. But it appears that identity and location are already known, but there are also location privacy risks in that the information inside the message may be more precise than what is available from the database, or that you can link multiple messages and tag paths. Now, what we're interested in is in reducing this amount of identifiable information in these log files. And how serious of a problem is that? Well, there are many examples where this has been studied. One example is medical databases here from Latanya Sweeney at CMU. This is an anonymized database of medical problems as it would be revealed to medical researchers, for example. And since there are no names here, it appears there are no privacy problems. But if you take a combination of these values, they together maybe and link them to a voter registration database, for example, they may be distinctive enough to identify an individual. And Sweeney has shown that that's possible in a large number of cases. There was a DoubleClick who is anonymously tracking web usage through cookies and other methods, was planning to link these anonymous traces to identifies records of store merchants. Another example of linking different databases. And there's also the difference that location information is the link between location and identity is often publicly available. Currently, the music industry is trying to track down file swappers, and in that case, they have to go through a legal process to reveal the connection between identity and IP address. Or they can find the IP addresses of users of these file sharing services, but to them it is unknown which user had a dynamic IP address at a certain moment in time. So they can only do that by subpoenaing DHCP log files from the internet service providers. In location information, in the case of location information, that may not be necessary. The information may be publicly available, and you can identify users without them noticing. Are there other threats? Well, yes. What we are looking at here is preventing the identification of queries in log files after the fact. So preventing automated massive data collection. You're not really looking at a targeted investigation into one individual as it may be conducted by the FBI or something like that. And I've talked a lot about application layer information. There may be tracking possible on wireless LAN at the link layer, and that's something I will look at briefly later in my talk. So here's an overview of the rest of my talk. I've shown you the privacy threat in location-based services. Now I will introduce my mechanism, automatic resolution control, and then go into an implementation of that mechanism in the wireless LAN architecture. And finally, I will talk about the future challenges in their work in terms of addressing continuous location tracking, addressing privacy in sensor networks, or addressing other types of data, other types than location. So the problem again is, how can we prevent that data linking when we want to reveal location information to an untrusted application service provider? So we want to use their service, we have to reveal information, but we do not want them to link it to an identity. And of course we need to maintain the quality of that service. The service can't just become useless to us. And there are many potential data sources that an adversary may have and that we don't know in advance. So the assumptions that we're making is, if that we have a location broker and that the location broker as well as the user's devices are completely secure and trustworthy. We will not look at security problems in this area. We will only look at the data that is available to the application service provider and what an adversary, malicious employees, or anybody who gets a hold of these log files could conclude. And also remember that we're looking at the sporadic query examples.
So where is, like in a network, where is the location broker?
Assume that it's in a network that the user trusts, such as the cell phone service provider in that case. And we assume that the cell phone service provider is more trustworthy than these application service providers because you have a longer term relationship, and you also have some communication privacy government regulation in that case. So for a cell phone service provider, you typically sign a 1 or 2 year contract when you get a new cell phone. So it can be expected that you actually take a look at the privacy policy versus I just want to use the service on the web real quick, and you don't want to study a lot of documentation in that case. Now, the key idea is to exploit user density information to reduce the resolution of the position information that is actually revealed to the application service provider. So if we don't use highly precise information such as 10 meter precise, but we use coarser information, then this linking to one specific user becomes a lot harder. And we could ask, why do we not just use zip codes? They are fairly coarse areas, but using coarser areas also reduces the quality of the service that you receive, and it may do so unnecessarily do so. How much should we reduce the resolution? Is there a static type of resolution such as 100 by 100 meters? Well, it depends a lot on population density in different areas. If you take the same resolution in Manhattan, you see there are a lot more buildings, a lot more people in that area than if you look at the outskirts of Boulder, Colorado, for example. And also it varies in terms of time of day, how many users are around on the streets, and so on. So what we are proposing is build a general solution that adaptively controls the resolution of queries or the resolution of the location information that is revealed to the external service provider, and do so based on the user density information in a certain area. Now, to find the optimal resolution that provides the best quality of service but maintains privacy, we have to define what privacy means. So our definition is k-anonymity. So a specific resolution, or we can look at that as an area. The area is k-anonymous if it includes your own position and that of k-1 other persons in that area. So another way to look at it is from the service provider's perspective, he cannot be certain which of these k individuals in that area, these k potential users, actually originated the query. And so if you, let's say your own position is this one here, and there's another user in that area, if you reveal this area here to the service provider, it would be too anonymous. But you could also choose a larger region, such as this one here. Now you have 7 users, and it would be 7 anonymous. From the service provider's perspective, it must also be all of these subjects must have been equally likely to have chosen that area. If he could be sure that this subject only would choose a smaller area and this subject only a larger area, it can be again linked to an individual and your privacy is lost. So how do you actually determine such an area? How do you choose that area? We use that through a cloaking algorithm that computes automatically computes the resolution. And if you look at the street map here, where the black dots represent different users, and the cross represents your own position before you originated query, the algorithm proceeds as follows. First, let's get rid of the street map so we can see the users a bit better. And then the algorithm starts out with a large region, for example, the region that the location broker covers. And you have to input the degree of anonymity that you desire, such the minimum of k, such as 5 in this case. And then the algorithm does a binary search for an optimal or close to optimal area. It subdivides the quadrant, or it subdivides the area into 4 quadrants, determines which of these quadrants the user is in, and if there's still sufficient user, more than 5 in that area, it subdivides again repeatedly until it finds here that this quadrant only includes 3 users, so below our threshold of 5, and then backsteps to the previous safe quadrant. Now we have identified a quadrant that is that includes more than 5 users and is relatively small. In this case, it actually includes 8 users because we step back to the higher resolution. And you could ask, why don't we just do a 5 nearest neighbor search of who are the 5 closest people around me and choose that area? Well, first it would be a little bit less efficient than a binary search, but also if you look at the users in this query, all of them should choose the same area to the service provider. If you do a nearest neighbors, this guy originated query would probably include neighbors on this side, so choose an area here. On the other side, you likely include neighbors here, so the areas would actually be different, and that's a conclusion that the adversary may make to identify who computed that area.
So it seems like so this k-anonymity is sort of a one-time test, right? Mm-hmm. It seems as though if you are allowed to check sort of someone's area at one time, and then in the future he has k-anonymity somewhere else, right? Very good chance that he'll be the only person who is here and there, and then his anonymity is gone, right?
That's why I made the distinction between continuous tracking services and location or sporadic queries. If you're only doing sporadic queries and you don't have any pseudonym that links 2 queries together, it's hard to determine that these 2 queries actually originated from the same user. Now, if you have that information, that two queries at different points in time are from the same user, then I have to agree with you. You can take an intersection of the different users and probably identify who originated these two queries. So the key is in making the individual queries independent, so that there's no information that links two queries together to each other.
Or to blow your queries from station at rush hour.
Yes. So the first question that we ask then is, if you use a mechanism like this, will you actually compute higher resolution than zip codes? If it's on the same order of magnitudes than zip codes, let's just use zip codes. This doesn't buy us anything. To do this, we looked at automotive traffic data. That's the best data on user populations that we could get, because there are many sensors alongside roads that track traffic volumes, and there are many traffic studies for road planning. So we downloaded data from USGS on different road maps in the Denver area, which also has a bit wider streets and thus is a more challenging area. And here you see two highway areas and two randomly selected residential areas. And then we looked into the traffic studies and came up with approximate traffic volumes on these different types of roads, and adjusted for different times of days based on the road sensor information. So now we could build snapshots of a traffic condition at a certain points in time, and using a large number of these snapshots where we ran our algorithm over them, we can compute the median resolutions that this automatic resolution control algorithm comes up with. Now here on the x-axis you see the median resolution, and the axis stand for these different different maps up there. You see for these highway maps, the median resolution is smaller than for the more residential areas here, which makes sense because on highways there's usually a lot more traffic. But the order of magnitude here is substantially less than the resolution on zip codes, and also it is similar to at least the initial requirements put forth by E911. I believe the initial requirement was 125 meter accuracy in about 2/3 of cases. So they have been changed subsequently, but they give an indication on what people believe to be a reasonable accuracy for some location-based services. So we conclude that this level of accuracy would be useful for at least a certain class of location-based services. On the y-axis, you see the actual level of anonymity that goes together with these resolution numbers, and the minimum was set to 5, and on average the areas that were computed included about 10 users. So from the service provider's perspective, there's an uncertainty. One of these 10 users has originated the query, but I don't know which one. Now, how would you actually implement something like that on wireless LAN? And specifically, we were interested in the question if you can you do without a location broker? It's not clear that every architecture will have such a location broker. The algorithms I just showed you were running at this level, and they assumed that the location broker has position information of all cell phones in a certain area. Now, if you use wireless LAN, how can you maintain privacy at the MAC layer and especially at the service layer? And how can you do so without any trustworthy intermediary? And again, we're assuming here that we're only looking at passive attacks based on log files that are taken at the service provider. We assume that nobody's actively attacking the system. So the key idea is here to use spectrum monitoring to infer the user density in different areas. Now we don't have the user population information from the location broker, so we try to come up with that information through spectrum monitoring. And we implemented that here this architecture are all different components that run on a laptop or could also be implemented on a PDA, so a user's trusted client system. And first we have a spotter that collects beacon information for positioning, but it also collects information on different clients that are within your radio range. To do this, we took a Prism 2-based wireless card and switched it into a monitor mode, which is basically a promiscuous mode that forwards all packets that are visible on that channel, not just the one that are addressed to your station. It also includes some debugging information, such as received signal strength for each packet. And we use this received signal strength to try to estimate an approximate distance of a user. Now, in most cases, you have plenty of abstractions, so estimating the actual distance is hard, but by calibrating the system for a certain environment where it's supposed to be used in, we can try to estimate an approximate maximum distance and err on the side of more privacy. The beacon information goes into a position estimator that knows the position of all access points in an area, and then based on which beacons are received and what their signal strength is, tries to estimate the position relative to these access points. Now, we have not focused our implementation on this part because there are plenty of systems available that do this much more precise by using different filtering algorithms. And we believe that we could plug in any of these systems as long as they are implemented on a client. Now, position, actual position, and number and distances of other users. We can infer the number by looking at different MAC addresses. Then goes into our cloaking algorithm, and I will show you in a minute how that works. Once we have computed a cloaked position, it can be forwarded to the browser, who assembles the location-based query and then sends it to the external service provider. First, we have to figure out how to estimate the distance of other users nearby based on their signal strength. And to do this, we calibrated the system for our lab environment. If you wanted to use a system like that outdoors, you would have to calibrate for free space assumptions or the specific environment that you want to use it in. But because our system is only running in the lab, we used our environment here. We took one sensor and recorded signal strength at different positions across our lab. And you see the results of this here, the received signal strength indicator versus the actual distance as computed on this map. And we can create a somewhat reasonable relative model, but what we use is this 95% confidence of the maximum distance. So for a given signal strength, we can compute the expected maximum distance based on that confidence interval. Now, how do you actually do the cloaking? How does that cloaking algorithm on one single client work? What we want to prevent is an adversary linking public data to your own that contains identity to this particular location-based service request. Now, the cloaking algorithm receives several distances for different users, and it's configured for a particular K, so you can choose the K smallest distance and then work with this radius. The the problem is that each client has a different local view and has a large degree of uncertainty about the actual positions of different users in that area. So if that is the view of one client, we could try to run our standard cloaking algorithm on this position, and we modify it a little bit by saying that we only subdivide areas if they completely enclose the circle here, all possible positions for the k-1 other users. So on the next step here, when we subdivide it, none of these quadrants encloses this complete circle anymore, so it would choose this quadrant here. Now, what happens if one of the k other users actually sits here? Now, his circle looks something a little bit different. They both have a different local view. There's no global view on the situation. And if you run the same algorithm with these assumptions, we would actually compute this largest area here because it doesn't fit into the smaller one. Now, if you as an adversary know what the positions of different users are, and you're trying to link the sensitive content to it, you can just run the same algorithm and find out which of these two users issued the request. Now, it turns out that under these assumptions, there is actually no possible algorithm that computes exactly the same area, starting with a different view of the world. And so what we can do is take a simpler approach and see, well, if we cannot absolutely determine such an area, let's just use a probabilistic algorithm which has a fairly high chance of coming up with such a good area. And you can take a much simpler algorithm that starts out with your actual position as the distance estimate, and then randomly displaces your own position within that distance estimate. And then as a cloaked area, we choose a larger circle that encompasses all possible areas, all possible positions of other users. So if you use an algorithm like that, we assume that these algorithms are known to the adversary, and one of the standard security assumptions, no security through obscurity. So the adversary sees a cloaked area, and from this public data that he has obtained from some other database, he sees an actual position of a user and his identity. So he can look at what the actual position of a user given from his database is relative to this cloaked position here, and try to determine what the probability is that the user here would have computed this position given that algorithm. So this is what we showed here. For the randomized algorithm and the discrete algorithm that I showed earlier, the probability based on this known subject relative distance to the center of this cloaked area, and this is symmetric. We only look at the radius, the distance here. Now, this shows the probability that if there were only two subjects in that area, that one known subject that I see in a database has issued that's the probability that the adversary would assign based on that information that the message originates from that one known subject. And you see that for the randomized algorithm, it is very close to 50%, 50% being the maximum uncertainty between two users. And then once you get too far away from the center, the cloak position becomes unreachable, and it is clear for the adversary that this particular subject cannot have originated the message. Compared to the discrete algorithm, you see here that the adversary can assign much higher probabilities. So here you can be 85% sure that the subject he sees in the database has originated that particular message if the subject is close to the center. So we prefer this randomized algorithm because it never reaches, the adversary never reaches this high certainty. And now I will talk a little bit about wireless LAN. Here the wireless LAN.
Where does the 50% really come from? Comes from
if I have two users, and so assume I'm looking at the worst case here that there are only two users. If you choose to have a larger case, 3, 4, or 5, your uncertainty would be much greater. If there are only two users and I have no further information, my basic assumption is that any of these users are 50% likely to have originated this message. And
so for 5 users, will it be a curve at 20% or not? Is there something different that happens with more users, or is it?
For 5 users, the variant is just the basic starting point would be at 20%. That's correct. So for the more users you have, the larger your uncertainty is. Now, before we looked at service provider log files, now we also, in the wireless LAN implementation, access points can also collect log files, and every station has a unique MAC address, so you can track their movements between different access points. And we looked briefly at this problem, and just to judge the magnitude of that and see whether there are easy mechanisms to counter that. We believe that the service provider tracking is more serious because the adversary doesn't have to come close to you, close to the area where you are. So there's an effort involved for somebody to actually going to that location close to you and then obtaining the log files there versus just looking at requests in a remote service provider. So what if the adversary has access to data collected at access points, and what he can do is track your movements across these different access points. A simple mechanism would be to switch MAC addresses whenever you're newly associated with the network. So whenever you shut your laptop down, boot it back up, when you come up with a new MAC address, then the adversary has difficulty in determining whether that's still the same user or not. And let's see how that helps. Here we took access point log files collected by Alejandro at the SIGCOMM conference in 2001 and analyzed how long users stayed on the network over this 4-day period. And on this curve, the baseline, you see how long different laptops were online. The way to read this curve is that at this point here, you can see that 90% of users were on the network for longer than 1 hour. So this is the total time where you can track, where you can determine the laptop's position. Now, if you switch MAC addresses whenever somebody logs onto the network, we're getting to this curve here, and where only 10% of users are then being tracked for longer than 1 hour. So only 10% of sessions last for longer than 1 hour. Now, from the adversary's perspective, they're not just MAC addresses that he can use to track a user. There's a lot of other information available. He could look at message content, see what destinations on the internet somebody communicates with it. But to do that, he has to actually dump dump network traffic, what he can obtain from the log files is signal-to-noise ratio, for example. And if you make the assumption that if somebody disappears from the network, then reappears, a new MAC address reappears, and it has very similar signal-to-noise ratio measurements as the previous one, maybe it's just a user that returned to his previous position. So if he then links these traces together, he can track users longer than in the MAC address switching case, and we're getting to this curve. But also there's a...
kind of like that curve depends on like some specific assumptions you made about like, you have to do some guessing in there, right? And you maybe, like if you do linear guessing...
The adversary has to do guessing, is that what you're referring to? Yes.
Right.
So
that's a curve you get with a particular algorithm for guessing, right?
Yes, that's the guessing there basically means if you see somebody reappear with the same signal strength, I will just conclude that that must be the same user. And on this graph you see that that guessing isn't correct in a lot of cases. So here you see the total of switches, MAC address switches at that conference at different access points on the x-axis. So the green portion of that bar shows you where somebody correctly linked a switch to the same user, but the red portion of that bar shows you where the adversary using that particular heuristic believed they are the same user, but actually they were completely different users.
So you had laptop people were running an algorithm where they kept changing their MAC address?
This is a simulation based on the log files recorded at SIGCOMM.
So then you put in a thing where you took the log files and then said, oh, now all of them change their MAC addresses.
So now I see somebody disappearing from the network based on this log file. And now I see somebody reappears, or the same MAC address reappears. Let's assume he just changed it in between to a randomly selected new address.
Yeah.
Then what does it look like to the adversary?
Sorry, I'm missing something. How do you change MAC addresses? I thought that would be hardwired into your laptop.
I looked at several wireless cards, and they have a hardwired MAC address in the card, but the drivers only use them as a default. So you can tell the driver to actually put a different bit string into that field before it gets sent out over the network, and that's how you can change.
Is that compliant with any standard? Would eventually lead to problems, right? Because the hardware authority that issues MAC addresses would not be able to work.
So there are potential dangers to that you can have you can have collisions, and the two laptops choose the same MAC address on the same network, but there are also collision detection mechanisms how you could find that out that's going on. I do not know if it's standard compliant. I do know that most Unix systems have a standard command to change the hardware MAC address even on wired cards.
So, but in general, there will also be a fixed mobile IP address which can be used as a handle by the adversary. So you have to hide the IP address as well, or else.
So I'm assuming that you dynamically obtain a new IP address whenever you start a new session on the network.
So when you say, oh, you see a new MAC address appear with the same SNR. Somehow, like you have some coarseness that you were measuring SNR by.
Yes, that's the
1, 2, 3, 6 dB or something.
That's the. I do not know exactly what the coarseness is in that case. That's the data I received from these particular access points used at that conference. So the data that was included in the log files.
All right.
So this is very dependent on that particular setup, on the user characteristics, how they moved around at that conference. but I'm showing you results to give an indication of what approximately the magnitude of that problem is. So, related work on location privacy. There's general work on privacy and ubiquitous computing by Jason Hong and Anand Day at UC Berkeley. They take more a human-computer interaction perspective on it, on how can computer users tell the system when they want to reveal sensitive information. And it's not just focused on location-aware systems, any type of sensor information that is collected there. So rather than having anonymous interactions, such as in location-based queries, they look at identified interactions and how to let the user specify what data to reveal and what to keep secret. There's work on k-anonymous databases by Latanya Sweeney at CMU, where they take static database tables, such as the medical database that I showed you, and then have algorithms that modify such a database table so it can be made public to researchers. And the difference is that you have a static table, a static database table, where the whole table is known while the algorithm is running, versus in my work, I first have to get an idea on what the user population actually is. I have to, using wireless LAN, I have to determine that, and then I also have a lot of uncertainty in the user's position rather than having specific entries in that table. There's work on privacy-aware data mining by Rakesh Agarwal and at IBM Almaden. He started off that field, and here the question is, how can you perturb information before you put it into a database, and then still allow data mining algorithms to work with that perturbed information and allow these algorithms to draw approximately correct conclusions about the distribution of values over a large number of users. So rather than executing a query for a single user, as I have described. And finally, there's a lot more work about privacy policies, specifically for location information. Hengartner and Steenkist at CMU have built access control systems where users can specify under what circumstances other parties can access their location information. And the IETF Geo-Privacy Working Group is working on standards mostly for cell phone service providers on how to implement these things. So now let's go to the challenges and future work. So in general, I believe that this privacy research is important because consumer backlash or misguided legislation can stop technological progress in a certain field, or for companies hamper their product deployment. And privacy is a very complex issue that requires technical solutions, but also social norms, legislation, and education. As a computer scientist, I'm mostly looking at the technical threats and technical solutions to these. Privacy enhancing technology research I see as informing consumers, legislators, and also business decision makers on what the problems in this area are. And here I have 3 ideas for future work on how to extend these systems. One is the problem of protecting paths of identified information. We have touched on this briefly in the problem of linking multiple queries to each other. What if you have very frequent location updates upstream, then can you still do these resolution control? Can you anonymize these paths? Likely the resolution that you will get is much less than the results that I've shown you, because now you have to look at a complete path rather than a single point, and you only have to include the users that actually travel the same path. And another way to look at it is if k-anonymity is too hard in that case, can you reveal identified information and only protect some sensitive parts of that path. For example, if this is a city block in so meaning that these are different houses and these are streets here. If you travel down that street, then enter a building for a while, come back out and travel on, maybe the fact that you entered this specific building is much more sensitive to you than that you traveled on that public street here. So can you build algorithms that can hide the fact which of these buildings in a certain area you entered? And I've done these feasibility studies on this and published that in the IEEE Security and Privacy magazine. Another area that I'm very interested in is trustworthy sensor networks. Sensor networks are small sensor platforms such as the Berkeley Modes or here the Mantis platform that Rican developed at Colorado. And they promise to reduce the cost of deploying sensors over larger geographic areas. So one application of this may be tracking positions of users in stores or alongside roads or possibly also in office environments. Now, if you look at applications that do not require user identity but merely statistics about user distributions, then can you build these resolution control anonymizing algorithms into the sensor networks? And the key challenge is, rather than having one centralized location broker, can you do so in a distributed, highly distributed fashion inside the network? Leverage the computational power of the on all of these different sensor chips to compute the level of detail that you can reveal and then store into databases. A sensor network like that could be certified under Federal Information Processing Standard, and so that the users have some certainty in that their privacy is actually protected when such a network is deployed. And first ideas on this I have published in last year's Hot Topics in Operating Systems workshop. And finally, this is BlueSpace, a smart office environment that integrates multiple different sensors, input and output devices to try to improve the user's comfort and productivity. So the system is basically sensing what the user does inside his office and how many users are present, and then reacts to that. This was a project I worked on for a year at IBM Research up in Westchester, and here you don't just have location information, you have many types of other sensors. What do you do about that kind of information? Can you use the similar approaches where you dynamically adjust the detail of information? That's also something I'm interested in for future work. So in conclusion, I've shown you my automatic resolution control mechanism that can strengthen the anonymity of location-based queries, and it can be implemented either at an intermediary such as the location brokers and cell phone networks, and probabilistically it can also be implemented on wireless LAN, running as a client on laptops. Now, these algorithms seem to, from the traffic studies I've done, they generate sufficient accuracy for many location-based services, and so I believe they are very useful. I've also talked about that I view research in privacy-enhancing technologies as informing consumers' legislation, business strategy of possible threats and protection. And finally, I've shown you what I see as the challenges in this field for protecting privacy in sensor networks, protecting path information, and addressing other contextual information from other types of sensors. that's the end of my talk, and I'm happy to answer any questions.